In today's assignment, we're going to look at the derivative. So the learning outcomes for this lesson are to calculate and interpret the secant slope, which can also be referred to as the average rate of change or average velocity. We're going to use the definition of the derivative to calculate the derivative, which can also be referred to as slope of the curve, instantaneous rate of change, instantaneous velocity, at a specific point. And we're going to identify points at which a function fails to be differential, either by using the graph or other information about the function, and determining an equation of the tangent line to a function at a specific point. The advice for learning these for mastering the learning outcomes are the following. So the difference quotient we actually looked at on the very first day of class. So for this point, right, you may want to reference topic A0. This is what we did on the very first day. So we saw that the secant slope is f of a plus h minus f of a all over h. This equation is not simplified until this original h that's in the equation gets canceled at some point during your algebra process. We also would refer to this as the average velocity. So if f of x, or f of t in this case, represents a position function, then if you look at the units when you calculate the difference quotient, your result will actually end up being a speed or velocity. When you're working with the difference quotient, it's often helpful to calculate and simplify if possible. So one thing that might be helpful, and we'll look at this today, is we might actually do some work on f of a plus h and f of a separately before we plug them into the difference quotient, because doing algebra in here can get a little bit nasty at times. The definition of the derivative of y equals f of x at x equals a can be written the following way. Okay, so when you see the a in this definition, what we're doing is we're finding the derivative at a known point. So what happens is your result is one value or one specific tangent slope. So your answer here is a single value, a single number. We're only getting one derivative at that one specific location. When the limit exists, right, when we actually get a result, we say that the function is differentiable at that location. If the limit for some reason does not exist, then we say that the function is not differentiable at that location. Other names for the derivative can be called the slope of the tangent line to the graph, the slope of the curve to the graph at that point, the instantaneous rate of change. So this is important. If you see any of these terms in like the instructions of a problem, they're all synonyms for just taking the derivative. So these things, these statements here, are interchangeable. And there's one more over here. One more extra statement that says the velocity or instantaneous velocity of f of x at x equals a. So I would add that to the list on the previous page. Assuming that your input variable is x, you can also write f prime of a as df dx. So f, right, is the name of the function. In this kind of more formal notation, you can see that the name of the function ends up here. So they're both involving f. So f prime is the same thing, right? df. The x in the denominator here is the name of the variable. So this is read as the derivative of f with respect to x. So this is telling you what the variable is. If we put this vertical bar and then here we have x equals a, it's actually telling you compute the derivative and evaluate it at a. So this is a much longer sort of notation that f prime of a is pretty concise. You can kind of see why we kind of prefer that. So if we want to break this one down, right, f is the name of the function, prime means derivative, and then you can see the a inside is saying take the derivative of the original function and then plug a into it. We can see that this notation Only thing that adjusts here is if I just change the name of the function. So if the function is now not named y, we get y prime of a, or dy dx evaluated at x equals a. The expressions of f prime of a and df dx at a are most commonly used when the function's name is f. The expression y is most commonly used in situations where the function name is y. So you can see it's just a name. We don't always use f for specific functions. We don't always use y for specific functions. They're almost interchangeable. At points where the derivative fails to exist, you see many different types of behavior. So a function would not be differentiable if there's a discontinuity, including asymptotes, sharp corners or cusps, or a vertical tangent line. And so we've actually given you a diagram here of two of these. So this is an example of a sharp corner or cusp, right? The other function that you're very familiar with that would have this attribute would be like an absolute value function, right? The absolute value is usually what's creating that point. A vertical tangent, so what's happening here is this graph is actually going straight down right here. So you actually would have a vertical line, and so the denominator of that slope would essentially be 0, and so you actually cannot take a derivative at this location where we have a vertical tangent. We would actually conclude for this particular graph, right, that this function is not differentiable at x equals 1. And one thing to keep in mind is this is not the same situation as a vertical asymptote. So remember, a vertical asymptote, the y values are trending to either positive or negative infinity. That's not what's happening here at all. The graph is just falling vertically straight down. It's continuous, right? But it's not differentiable in that region. An equation of a tangent line to the graph y equals x at point a comma f of a in point slope form looks like this. So this is the exact same formula that you're used to seeing in point slope form. It's just now we're calling a f of a x1, y1, and f prime of a, right, is your slope. So we're just introducing a new notation, but it's the same point slope formula that you've been using all along. So just a quick little note for students who might have some prior calculus experience. There are some shortcuts to calculating derivatives, but you will not be able to use those while working on the limit section, so Unit B. We will get to them later, but it's important for us to think about where derivatives come from, and we will get no deep understanding from applying the shortcuts. So this is a very important process in learning calculus, so we have to sort of crawl through the mud a little bit before we get to work with our shortcuts.